Hi, I want to go through the first 5 problems of the review for exam 1. So the first problem for the review is this problem to find the average velocity of the function over this interval. Now, to find the average velocity of a function, the average velocity is a change in distance over a change in time, assuming that the function you have is a distance function, the distance of, some particle as a function of time. That's not really given here, but we'll pretend that this function y, which is a quadratic, we'll pretend that that function gives the distance traveled by some particle as a function of time. Time here won't be represented by a t, but it's represented by x. So we're still using the same idea of change in distance over change in time, which is the same as a change in y over a change in x. It's really the slope of the secant line through these 2 points. So the change in y over this interval will be the function at the upper bound subtract the function at the lower bound over the difference in the x values. And if you just do the substitution into the function, you should get this result. And then, of course, when you do the arithmetic, you should get -34. So what does that mean? Well, we don't have any units here for this function. I mean, we don't have like feet per second, in terms of travel time. This distance function doesn't give any kind of units, but if it did, suppose this were the distance traveled as a function of time, and it was the distance measured in, say, meters, and it was and time was, this was 5 seconds, this was 6 seconds, so this would be a change in 34 meters in the negative direction over per second. So it would be -34 meters per second as a result, and that would mean that this function's actually decreasing, going down. And if you graph the function, you'll see that it's decreasing over this interval. So now our job is to use the graph to evaluate the limits. So we have a bunch of limits here. In the first case, we want to look at the limit as x approaches 2 from below 2. So that's this section of the graph. So as x gets close to 2 but is strictly smaller than 2, those points are mapped to this section of the graph, and the y values for these points on the graph, those y values will get as close to 0 as we want. So this first limit is 0. The next limit we want is the limit as x approaches 2 from above, right? That's what that plus sign means. So if we're approaching 2 from above, that means we're looking at a sequence of points x that are strictly larger than 2. So if we look at the image of this sequence of points, those points are mapped here on the curve. And so if you consider the y values of those points, well, if you project the curve onto the y-axis, the y values of those points are here on the y-axis. They are getting as close to -1 as we want. Those are the y coordinates of these points. So as x gets close to 2 but is strictly larger than 2, the y values are getting close to -1 but are strictly less than -1. In the limit, this would be equal to -1. In the next question, we want to know what's the limit as x approaches 2. Well, in order for this limit to exist, we would need the lower and upper limits both to exist and be equal. We see they both exist, but they are not equal, so this limit does not exist. And the last question is not a limit question, it's a function question. Where is 2 actually mapped by this function? That's indicated here with this filled in circle. 2 is actually mapped to 0, so f of 2 is 0. Here we need to find a limit, and this limit, the function here is a polynomial. It's a linear function, so this function is defined everywhere. There are no problem points at all whatsoever for this function, so we can evaluate this with direct substitution. So if you use direct substitution here, then you would just substitute x equal to 18, and the result's -21. Here, for problem 4, we are given a limit x approaches -9 of f, and a limit of x approaches -9 of g. And the question here is to find the limit as x approaches -9 of this ratio. So we know by properties of limits that the limit of that ratio is going to be the ratio of the limits. And each of those limits is defined and exists. And so we would just substitute, and the result is 9/4. And this last question, we are given a piecewise defined function, and this piecewise defined function is linear over both pieces, actually. So this function f of x is this line, -2x plus 2, for x less than 6. So if you graph the line -2x plus 2, that line is like this green line here. But that green line, we only want that, the function is only given by that formula for x smaller than 6. So if you graph the whole line, you would want to erase everything that's larger than 6. And since this is a strict inequality, when x is equal to 6, the function is not, the function is not given by -2 times 6 plus 2. That's what this open circle indicates. This open circle indicates that this point is not on the graph. The point 6, -10 is not on the graph. Where is 6 mapped? 6 is mapped by this formula, which would be what, 27? So f of 6 is actually 27. So this ordered pair is the ordered pair 627, and that's indicated with this filled in circle. And for x larger than 6, we have this line, and that's the magenta line here. Okay, so that's the graph of the piecewise defined function. Now in terms of the limit, our first job is to figure out the limit as x approaches 6 from above of this function. Now if x is getting close to 6 but is strictly larger, then we're looking at a sequence of points. We can think about a sequence of points strictly larger than 6, but getting close to 6. And so that's indicated, I'm waving this arrow at you. That's this area. Now where are these points mapped? Well, those points are mapped via f to this part of the graph. And what are the y values here? Those y values are getting as close to this point as we want. And we know that the value here is 27. So as x gets close to 6 but is strictly larger than 6, and again, if you wanted to make a table, you could look at a sequence of points like 6.1, 6.01, 6.001, that sort of thing. You would see that those y values are going to get as close to 27 as we want, because for x larger than 6, we're using this 4x plus 3 formula. So this limit, of course, is going to be equal to 27 because the y values get as close to 27 as we want. What about the limit as x approaches 6 from below? Well, as x approaches 6 from below, we're approaching 6 through values of x that are less than 6. So values like 5.9, 5.99, 5.999, that's a sequence of points that's getting close to 6, but all the values are strictly less than 6, and those values are mapped via the function to this line. And as we get close to 6 but are strictly smaller than 6, we will get as close to -10 as we want. So that means this limit is -10. And so in terms of the limit as x approaches 6 for this function, well, that limit is defined provided the upper and lower limits both exist and are equal. We see the upper and lower limits both exist, but again, they are not equal. We saw this before in this set of problems, and so this last limit does not exist.